Hey, welcome to another video. So I always hated it when I learned something and never learned what you would ever use it for. So now I gotta tell you, with quadratics, there's a lot we can do, but not a lot of really neat stuff. You need like differential equations, really cool stuff, and higher math than that. And calculus. But I can give you a couple examples to show you how this would be used, or some very basic things to say this is actually useful. So we're gonna go through three very quick examples on when you can use the idea of parabolas to solve some equations. One business, one area, real life example there, and then one like projectile motion. So here's the main thing that you need to understand though. This is it. If I asked you what the maximum value of a downward opening parabola, where that would be located, you would hopefully understand that a maximum value of a downward opening parabola would be located at its vertex. And the minimum value of an upward opening parabola would again be located at its vertex. So what a vertex does, if you ever asked to find the maximum height of a downward opening parabola, use the vertex formula. If you're ever asked to find the minimum height of an upward opening parabola, use the vertex formula. Of course, we really can't find the maximum height of an upward opening, that's infinity, or the minimum height of a downward opening, that's also infinity. But the vertex will give us the minimum for an upward or the maximum for a downward opening parabola. We're going to use that like 3 times in these examples. So let's take a look at the first one. We're going to talk about business for a little bit. So let's say that you have this business and you've done some product research and looked at your economics and determined that, revenue is pretty easy, but revenue is determined by how many items you sell times the price of each item. So if my price is $10, it never changes, and I sell 20 items, 10 times 20, I'm going to have $200 in revenue. This is not talking about cost, so we're not doing profit, this is very basic. Revenue is this idea of if I have X items, X times the price of each item is going to give you what's called revenue, how much money I'm bringing in. Let's imagine that your price changes the more items that you put out there. Now this is oftentimes true. If we flood the market with stuff that we're making, the price is going to decrease because we have to lower the price to sell it depending on supply and demand. So let's say that the price for our items is negative 1/3 x plus 100. So for every item we sell, this is, did you see it? Oh man, did you see the negative slope? Like this is a downward sloping linear price decrease. So every item we sell lowers the price of the items just a little bit. You might go, that's crazy. Why would we ever sell stuff if the price decreases? You're still making money here. So you're still making stuff, but you're lowering the price. It's kind of the idea, would you want to make a product that's super expensive and sell a few of them? Or make a product that's super cheap but sell a ton of them? There's a trade-off there, right? We might not want to make this super expensive product that we can only sell one of, because what if you don't sell it, or you've cost a lot in research and development, you might not recuperate all that, or we might not want to make an item so cheap that we sell 1 billion of them, but then maybe we're not making anything because we're spending all our money making our products. So anyway, there's a trade-off there. So let's say that for our price, every single item that we put out in production causes the price to have to decrease. What we're going to try to do here, we're going to try to find out the maximum revenue. So let's put these pieces together. If revenue is X times the price, and we have a price of negative 1/3 x plus 100, hopefully you see that I can do a very simple substitution and say, hey, revenue then, if I want to find my revenue, I just need to multiply the number of items I'm selling times the price of each item. Number of items I'm selling times the price of our item. That gives us a very nice look at a revenue function. Now, what would we do? Let's see, what are we trying to do? Number one, what I want to understand is what this looks like. So let's distribute it. Let's see what it looks like. Oh, there it is. So our revenue is negative 1/3 x squared plus 100x. In your head right now, you need to be thinking, this is a downward opening parabola. Would I be able to find the minimum value? No, the minimum value is going to be practically zero. You wouldn't continue to make items and go into debt just making items. Actually, businesses do that all the time, but we wouldn't want to do that. So there's no finding the minimum value of this downward opening parabola, but you could certainly find a maximum. We really wouldn't want to minimize our revenue. We'd want to maximize our revenue. That's possible. Here's what this says. As I keep creating values, what's going to happen to my revenue? It's going to climb, it's going to peak, it's going to fall again. That's what's going to happen because my price is decreasing as I'm increasing the product, but I'm selling more products, so I'm getting money from that. Eventually, there's going to be this peak. That's the idea of using parabolas to find a maximum or a minimum. So we have that. Now, one thing you might be asked is, what's the domain? Like, what would the domain be? Well, we would want our revenue to be positive. And so we find two x values that keep our revenue positive. We would want, this is going to go back to the last section, our domain is we want our revenue, we want that to be above zero. We'd want to at least break even by doing this, but that would be that negative 1/3 x squared plus 100x would be greater than or equal to zero. Okay, well, how would we solve that? The same exact thing about quadratic inequalities that on the last video. We'd say, well, that's a downward opening parabola. We're trying to figure out where it is above the x-axis. That's what we're looking for. If we are able to find our x-intercepts, then we can determine between what two x values our revenue will be positive. So we can do a couple things. We can do something like, let's multiply everything by -3. We could do that. We could factor out the negative and then not have to change the inequality by keeping the negative there, just find our the x values. We can do that too. It doesn't really matter. I'm going to divide out the negative, but I'm going to multiply everything by +3 as well to make our I'm going to factor out negative x actually. So negative x and take a 1/3 x plus 100. That's probably the easiest way to go. If I take a look at this, the zero product property says that one of my x-intercepts, if I just think of this as negative x, 1/3 x plus 100 is equal to 0, I know that the x-intercepts, where this parabola would actually cross the x-axis, I want to find that and determine where I'm above or below it. X would equal 0, and 1/3 x plus 100 would equal 0. If I subtract 100, oops, got to fix that. That would be bad. If I didn't mention it the first time, check your signs. So I made a mistake here. I factored out the negative. It happens all the time. I factored out negative x because we have a GCF. I screwed this up, so factor out negative x. I've got a positive 1/3, then I have a minus 100. So I keep that. I use zero product property. 0 would be set equal to x, or x equals 0. 1/3 x minus 100 sets equal to 0. If I add 100, multiply both sides by 3. Between these two x values, 0 and 300, is where my revenue would be positive. We do not want to produce less than 0 items. That's impossible anyway. We don't want to produce more than 300 because according to our price would start getting so, our price would end up, price times our amount that we sell would end up being negative. We don't want to start losing money on this. And so our domain would be 0 to 300. If we produce 0 items, well, then 0 times, I don't care what the price is, you're not going to make anything. Your revenue is going to be 0. If we produce 300, your revenue is also going to be 0. I hope that makes sense. We had this downward opening parabola. We said, where is our revenue going to be positive? That's what our domain needs to be. We don't want to be losing money here. So because that is a quadratic that's downward opening, we can determine where we are above the x-axis. This goes right back to the last section. I hope that you're seeing it. I did a little different this time in factoring the negative x incorrectly the first time. fixing my sign and then saying, hey, we would cross the x-axis at 0 and at 300, and we're looking for where this downward opening parabola is above 0. That's between these two numbers. That's our domain for this problem. Could you do something like find out how much revenue you would make if you sold 100 items? That means that we'd go up here and just plug in 100. So if we did this, if we figured out the revenue for 100 items, we would just plug this in and figure out what that would be. And what I got out of it was $6,666.67. Hopefully I did my math right. Squared 100 multiplied times negative 1/3, then added 100 squared. So if we sold 100 items, that's what we're going to be making out of it. Now let's move on. What would our maximum revenue be? That is the idea of understanding that if this is our revenue function and it's a downward opening parabola, where would our maximum revenue be? Minimum would be 0. Because we cut that off at our domain. If we went outside our domain, we would make negative money. We don't want that. So 0 would be our minimum. We don't want minimum. We want to make maximum. We're going to go into business and try to provide something good for that people are going to really want. Well, we want to make it worth our time. So we want to make the maximum revenue. At least that's what business people want to do. So how do you find the maximum for a downward opening parabola? That's got to be at the vertex. So we're just going to use the vertex formula. So we're going to use negative b over 2a, figure out that x value, plug it into our revenue, and that's going to give us the maximum revenue and how many items we need to sell to get that. So negative b, if we go back over here, we look at our revenue function. Our revenue function is negative 1/3 x squared plus 100x. Even though this doesn't have a constant or a c, we have an A and we have a B. So for our vertex, we'd have negative B all over 2 times A. Don't forget that's negative 1/3. You cannot change those signs, not with the vertex formula. So what in the world is that going to be? One thing, because we have a complex fraction here, we can multiply both the numerator and denominator by 3 or negative 3. If we do that, multiply by 3 over 3, then we get maybe negative 3, doesn't really matter. Negative over negative is going to be positive anyhow. We're going to get 300 over 2. And that gives us 150. So when we take that 150 and we evaluate our revenue function at 150, this says if we sell 150 units, that's what the X means, how many things you're selling. If we sell 150 units, then we're going to get this amount of money, this amount of revenue from it. So take your 150 and we're going to plug that in to right here. So take your 150 and put it for your R of X function. That says we'd have negative 1/3 times 150 squared plus 100 times 150. And it looks to me like we got about $7,500. So what that says to us, according to this model, if we take our amount of items we're selling times the price of each item, that's called revenue. We know that's a downward opening parabola. We can figure out where our revenue is positive. That is an inequality. That's a quadratic inequality type of an issue. Find out where your x-intercepts are, determine that this is saying where are we above the x-axis, but where our maximum is for a downward open parabola is the vertex. So we find our vertex. This tells us 2 things. This says how many items we need to sell to make our maximum revenue and how much revenue we actually get. Now the last thing, what is the price that you would need to charge to get your maximum revenue? So we already know we need to sell 150 items, but because we have a price function, we can plug in our 150 and it's going to tell us what price we should put these at. So this is our price for maximum revenue. We take our negative 1/3 times 150 plus 100. Let's see. 1/3 of 150 is 50. So that'd be negative 1/3 times 150 is negative 50 plus 100 is $50. So our price would be $50. What we determined here is that in order to get the most amount of money, we'd be selling our products, all 150 of them, for $50 each. I hope that makes sense, that you understand the nature of downward open parabolas. The vertex is the maximum. That's it. All right, let's move on. So I need to make a really nice garden, and I have 3,000 feet of fence. It's going to be a big garden. Here's what I want to know. If land is not limited to me, which it is, but if it wasn't limited to me, let's imagine that I wanted to get the biggest area possible. How would I do it? Well, if we have 3,000 feet of fence for a rectangular area, we need to find the maximum area. Here's the idea. What we're going to do is we're going to call one of these sides X, one of these sides Y. We're going to find the formula for a perimeter. Now, since we have 3,000 feet of fence, that is our perimeter. Like, we're going to use all 3,000. Then we're going to find a formula for area. The perimeter is going to act as our constraint. We can't get above 3,000 feet of fencing or below 3,000 feet of fencing, and our area is the thing we're trying to maximize. So this is going to be this way. We're going to draw a picture. We got it. We're going to make one of these sides X and one of these sides Y, because they might not be the same here, dimensions. We're going to find our constraint and the function we're trying to maximize, and then do a substitution. So what a constraint does, a constraint says, what are you limited by? So constraint has the idea of you're limiting something. We are limited by, not the area, we want to find the maximum area. That's not a limiting factor. We're limited by the perimeter. So if we can put that in a function, in a formula, or an equation, and we say, all right, what are we limited by? Perimeter. How much perimeter do we have? 3,000 feet. And find an expression that represents that perimeter. So I know that 3,000 feet is going to make up all four sides of my rectangle. That's 2 x's plus 2 y's. So I hope that makes sense, that our perimeter, 3,000 feet, is taken up by 2 x sides and 2 y sides. This is called your constraint because it's what's limiting your ability to make more or less area. Now, we can automatically do a couple things like simplify that. We could divide everything by 2. That's totally fine. But that's going to show up when we make our substitution. Well, that begs the question, what substitution are we making? The way that these problems, these maximization and minimization problems, which you're going to get a ton of in calculus, is find a constraint. We've got that, the thing that's limiting your problem. Find a formula for what you're trying to maximize. Well, what are we trying to maximize? Area. Do you know the formula for for the area of a rectangle? Yeah, sure. We know that area is x times y. So we've labeled x times y. We don't know if they're the same length sides. We don't know how they're related. We don't really care. But in order to figure out an equation that has 2 variables, you need 2 equations. One is a limiting equation called a constraint. The other one is the one you're trying to maximize. Use your constraint to substitute into the formula or function you're trying to maximize. So because this our constraint limits us, we say, hey, our area is x times y. We need to substitute for one of those variables. It really doesn't matter which one we substitute for, just one of them. So take your constraint and solve it for a variable you want to maximize. In this case, we're going to go, all right, I'm going to solve this for y. Why? Because I like solving for y. If I do that, I would subtract 2x and divide everything by 2. This right there, 1,500 minus x equals y, that is what we can replace inside the function I'm trying to maximize. So instead of a equals x times y, I can say a equals x times y, but y equals 1,500 minus x. If we distribute, and write this appropriately, like in order, we get sort of the same exact look as what we got in our revenue problem. We have this downward opening parabola that represents our area. All we're trying to do is find the maximum. So if you think about this, where does the maximum happen on a downward opening parabola? It's got to happen at the vertex. All we're going to do is find the vertex. We're not going to worry about the domain here. The domain would kind of be a natural domain of you got to be greater than 0. You can't have a side length of a fence that's negative. So it's kind of an obvious statement. But what we're going to do is, and we can't have an area that's negative, so it'll limit us. But anyway, we have this downward opening parabola. We're going to find our vertex. That'll give us our maximum area. So let's do that. Based on the fact that we have this negative x squared plus 1500x, our a is negative 1 and our b is 1500, our c is 0, but that doesn't matter for a vertex. So negative 1500 divided by 2 times a, 2 times negative 1. That looks like 750 to me. So 1500 divided by 2 is 750. The negatives simplify to a positive 1. And now the actual area. We're going to need more space than that. The actual area. What that says is that your x is going to be, this side length is going to be 750, looks like feet long. Well, according to our area function, we can plug in 750. It will tell you what the maximum area is. So take your 750 and evaluate a of 750. Make sure that when you do this, you plug in 750, you square that first, and then you change its sign. There's no parentheses around that negative. So 750 gets squared and then made negative, and then you're going to add 1500 times 750. And it looks like we get 562,500 square feet. So with a dimension of our x side being 750, we're going to get this as our maximum area. This is our x because that's the variable that we had this area in terms of. This is our max area. Now, you're probably going to be asked to find the y as well. Just take a look at your constraint. Your constraint should be solved for the variable you are missing. So hopefully it's not a surprise to you that the area that's the greatest type of a rectangle is a square. A square develops the greatest area for its perimeter. So 750 subtracted from 1500 is going to also give you 750. So our dimensions are 750 feet by 750 feet. And sure enough, if you take 750 times 750, you get that right there. So that's the way we'd find the maximum area for some sort of a measurement like this. One thing that people often will do here to make it a little bit more interesting is imagine you only had 3 sides you need a fence because you have like a river here. Well, the same exact thing would happen. It's just your constraint would change. If you had a river on one side where you didn't need fencing, then you would just have 2 x's but only 1 y. It's actually easier to solve. Subtract your 2x, make your substitution, do your distribution, and then you'd find your vertex with the vertex formula. That's about it. Just remember that that's going to be an x measurement, and your maximization, this is your max area. You are finding the vertex of your area function. That gives you a dimension of one side and the actual area if you plug it into your function. Okay, and our last example, I'm not going to do much with it. I just want you to take a look at this. It's going to be pretty nasty, but that would be the projectile, the height of a projectile, h is our height, for some sort of projectile starting at 45 degrees with a 2,000 foot per second launch. So if we wanted to find out a couple things about it, I'm just going to talk you through this. If you want to figure out how far it goes, so this is according to how far it is away from where you launch it, the height according to how far away you launch it. If you want to figure out how far it goes, what its, let's say, effective ranges. What is ranges? We'd set this function equal to 0. So set this equal to 0. You want to figure out when it hits the ground, right? So when it hits the ground is the distance of its trajectory. So if you set this equal to 0 and solve, that's a quadratic. You can do quadratic formula, you can factor, a whole bunch of things to do there. But anyhow, that's how we figure out how far this would go. Set the height equals 0. So function equals 0 and solve for x. If you want to figure out its maximum height, well, then we would say, find your vertex. If you want to figure out the maximum height this projectile reaches, then you would have your A is this nasty thing, and your B is 1. So on your vertex formula, you would have -1, that's negative B, over 2 times -32 over 2,000 squared. That is what your vertex would look like as far as your x coordinate, and then you would figure that out and plug it into your function to figure out your height, and your height would be right there. I just want to talk through that because that's a somewhat common problem for people to encounter, much more common as an area or like a business type of problem. So I hope that makes sense. Hope you understand the nature of minimums and maximums on using your vertices for parabolas. I hope I've come up with some interesting examples for you, and I'll see you for the next video.